Okay, so it's a pleasure to introduce the first speaker of this afternoon, Shira Tanny from Weizmann Institute in Israel. And she will talk about Viterbo's inequality and Finsler systolic inequalities on RPN.
Okay. First, thank you very much. I want to thank the organizers for inviting me. And this is my first time in Rio, and I'm very excited. The second thing I want to say is please stop me at any point if something is not clear or you have any comments. And then the third thing I want to say is that the new things I'll say today is a joint work with Julian Chaides, and it is very much in progress. It's so much in progress that I would even say it's in the beginning. Last summer I was at a conference, and one of the speakers said that the conference doesn't always come in the right time for the project that you want to talk about. But I actually think it is a good time, because I'm kind of hoping to learn new things here in this conference that would help me to kind of push this project forward. So we'll see. Okay, so the story is basically about an attempt to relate systoles in Reb dynamics, as Alberto told us in the first talk yesterday. So in Reb dynamics, we have periodic orbits. Many times they are contractible. And what Julian and I are trying to do is to relate them to systolic inequalities for non-contractible loops. So we kind of want to reduce this homotopically trivial but dynamical problem to kind of somewhere we can use topology. Okay, the big picture of what we're trying to do is the following. So on the Reb side, we have Viterbo's inequality, which I will recall. So this is the big picture, and then we'll zoom in. So this is basically a systolic inequality for Reb dynamics. So Reb systolic inequality. Now this Viterbo's inequality it has a connection with a question in convex geometry that is called Mahler conjecture. And so there we have an arrow like this. It's actually an if and only if you restrict. So I'll say more about all of this in a moment. But if you look at some symmetric products, there is kind of an interpretation of this problem to this problem. And this was done by Archstein, Avidan, Karasev, and Ostrover, who is here. And so this is one side of the story. And then the other side of the story is a very nice paper that relates, basically does a reduction from a systolic inequality on RPN to the Mahler conjecture. So this is a conjectured systolic inequality on RPN. And the systolic inequality for Finsler metrics, or maybe I should say for reversible Finsler metrics, was shown to imply the Mahler conjecture. This is by Alvarez, Paeva, and Balachev, who we heard a moment ago, and Zanev. Okay. So if you start from here and you kind of go along these arrows, you end up here at this Viterbo inequality, and I will explain later how in this particular case it is, well, Yaron also touched upon it, like it's a problem concerning billiard dynamics for flat metrics, okay? But for more general domains, if you want to consider this Viterbo inequality, you can think of it as billiard dynamics for non-flat metrics. Okay, so what we are trying to do basically is we're trying to draw an arrow like this. So this is a question. And we're kind of hoping to basically extend the class of dynamics for which we can reduce this Viterbo inequality to this conjectured systolic inequality, which was proved in dimension 2. I will say more about it afterwards. Any questions so far? OK, so let me start zooming in, and I'll start with this side and basically go to the right. OK, so let's recall Reb systols. So let's assume, well, some of you probably remember that Alberto was giving us kind of 2 very important examples or classes of Reb dynamics, right? One of them was star-shaped domains in R2n or convex domains in R2n, and the other was cotangent bundles. And I'm going to basically do a mixture of these 2 attitudes. But let's start with the first one. So let's let X in R2n be a convex domain with smooth boundary. Then the Reb flow on the boundary of X is the flow of the vector field R, called the Reb vector field, and it's determined by the following equations. So basically, its direction is determined by the kernel of d lambda, and it's normalized such that lambda of it is 1, and here lambda is the primitive of the symplectic form that we saw. So sum of xi dyi minus yi dxi. So it's primitive of the standard symplectic form on R2n. But maybe let me give another description that might be more intuitive. So alternatively, you can think as R as some rescaling of I times n. So this I is the complex I when you identify R2n with Cn. And then this n is, maybe I'll call it n hat, so it's not the dimension. This is the normal to the boundary. So the picture is, if this is x, well, that's the boundary of x, and this is x, then we have here normal, and then when we apply I, we kind of rotate it, so it's I times the normal. And then we follow this kind of direction, but we normalize it so that, so it's a rescaling such that periods of periodic orbits coincide with the areas of enclosing disks. So the period is this area here. So this is completely analogous to unit parameterization in Riemannian geometry, where the period is the length. Here, the period is the area. OK. So now we have this vector field. We have the flow of the vector field. And we define the Reb systole. I think it was C of x. We define it to be just the minimal period of a periodic orbit on the boundary. OK. So given this quantity, there is basically an inequality called Viterbo's inequality that appears in Viterbo's conjecture. So let me state the conjecture. So there was Viterbo's conjecture that says that whenever we're in this situation, so x is convex, then the following systolic inequality, systolic ratio. So C of x divided by the volume when you properly normalize it. So square root of n and then n factorial volume of x. So I should say that unlike Alberto, I put the square root here like the previous talk we saw today. And then this n factorial is just because I measure volume with respect to 1 over n factorial omega to the n instead of just omega to the n. Okay, but we divide it by the volume properly normalized, and then the conjecture is that this is bounded by 1 for all convex domains. Now, a teaser to Pazit's talk on Thursday is that this is wrong. So she and Yaron found a counterexample to this conjecture. But there are actually a lot of positive results. So there are kind of a bunch of classes of convex domains for which we know it's true, or we hardly believe that it should be true. And then basically now we're trying, there are several questions that we ask around it. One of these questions is for what is the correct class of convex domains, or of domains generally, for which such an inequality holds. So basically this inequality says that the maximizer or the optimal is the round ball. So we ask what is the class of domains for which the ball is a maximizer. Okay. One of the, I think, most important classes, or probably the most important class of positive results for this conjecture comes from this connection with the Mahler conjecture. Okay, so let me state this connection. So this is let me first say the Mahler conjecture and then the connection. So the Mahler conjecture states the following. If you have a convex domain that is centrally symmetric, so there is a non-symmetric version. I'm not going to discuss it. So k is equal to minus k. Then the conjecture is that the volume of k times the volume of its dual is bounded by 4 to the n over n factorial. So here the dual is the usual polar dual in convex geometry. It's just all of the y's such that inner product xy is bounded by 1 for all x and k. Or it's the unit ball of the dual norm to the norm identified by. Oh, sorry. Oh, thank you. Yeah, sorry. At least that. Okay. Right. So the connection to Viterbo was discovered by Rothstein, Avidan, Karasev, and Strover. And they proved that the Mahler conjecture is equivalent to Viterbo's inequality for x that is equal to a product of k times t. So here, x is in R2n, and each of these guys is in Rn. One of them is in the x coordinate space, and the other one is in the y with respect to the form I wrote over there. So such that these are centrally symmetric and convex. So t equals minus t, and they're both convex. So in particular, these products, they have kind of a Z2 times Z2 symmetry, right? So they are Z2 times Z2 symmetric. Okay. Any questions?
Is symmetric assumption necessary? Is it false, like in Mahler conjecture, for example? Is it not the false?
So there are interesting works about trying to connect the non-symmetric Malloy conjecture to this Viterbo, and essentially the conclusion is that it's not possible. Yeah. And these were before we knew that, okay, so maybe I should say, well, I don't want to say too much about the counterexample, but it is some kind of a product with non-symmetric domains, but the works that showed that Malloy cannot be deduced by Viterbo were before this counterexample. So even if Viterbo was true for non-symmetric products, such a reduction is still not possible. Okay. Right. So the idea behind, or some of the ideas behind this reduction, or an important ingredient in this reduction, is an interpretation of the Reb dynamics on these non-smooth domains, right? So the boundary of k times t is not a smooth hypersurface. And it's possible to interpret the dynamics, the Reb dynamics, well, to define it first, and then to interpret it as billiard dynamics on a table which is equal to k, and a geometry that is determined by t, like Yaron was explaining. So maybe let me kind of make a definition of this billiard dynamics in a slightly more general setting than this product. So let me define. If we have k in Rn, this is our table. And we have a Finsler metric on it. Right, so it's just a kind of a field of convex domains over each point in the tangent space to this guy. Then the billiard dynamics on k with respect to f, is given by, well, you go along geodesics in the interior. And the reflection law is determined by this Finsler metric essentially in the following way. So if this is our k, and here we have a point x, a point y, and a point z, right? So we have a geodesic segment from x to y, and then a geodesic segment from y to z. And xy is a proper reflection of, sorry, yz is a proper reflection of xy if y is a critical point of the distance with respect to f of xy plus distance of yz. So basically all I want to say is that the metric determines the reflection law, and yeah, it's given by some critical points of length functional. Okay. All right.
And geometric is not constant.
So yeah, so for in this case it is, and then I'll talk about a case which it isn't in a moment. But in this definition, it doesn't have to be constant. So it's any Finsler metric on the table. Okay. All right, so basically this interpretation of the wave dynamics in terms on products in terms of billiards, let me write it down. So this was done by Ashton, Avidainen, and Strover, and they proved that the Reb systole of the product is simply the minimum length. So it's a minimal length, okay, maybe I'll say in a moment, of a periodic billiard trajectory on K with respect to the flat Finsler norm, which is given by norm T dual. Okay? And this dual is not confusing because basically the thing that helps understand it, I think, is that K times T is simply the unit cotangent bundle so this is our X, right? Of K with metric, which is given by norm T dual. Okay. So maybe an example is if your table is an ellipse, so if K is an ellipse and T is the ball, so it determines the Euclidean metric, then the minimal periodic billiard trajectory is kind of a two bounce between along the short axis. And that would be the length going back and forth will be the Reb systole of the product. Okay? Any questions? All right. So essentially, what this reduction says is that the Muller conjecture follows from a systolic inequality for billiards with a flat metric, right? So billiards on convex table with a flat Finsler matrix. Now there is let me now go kind of continue going rightwards in this diagram. So now I want to tell you about this the work by Alvarez, Paeva, Balachev, and Tsanev that basically proved the reduction from this Muller conjecture to this conjectured systolic inequality on RPN. And then later on, what we want to do is to relate it to relate this RPN conjecture to a systolic inequality for billiards for non-flat metrics. Okay. So let me tell you what this RPN conjecture says. So we saw in the previous talk before lunch that there is a Poo's inequality that basically gives a systolic inequality for, I think, Riemannian metrics on RPN. And you can ask the same thing for Finsler metrics and in general dimension, so in higher dimensions. So let's suppose, but reversible Finsler, that's important. So suppose that reversible Finsler metric F on RPN. Let's assume that it has volume V. Then the claim is that, or the conjecture is that it has a non-contractible, so it's a homotopical systolic inequality, non-contractible loop or geodesic. Let's say closed geodesic of length bounded by, well, let's properly normalize it. So it's nth root n factorial v over 2. So if we want to write it in terms of the systolic ratio, so equivalently, if we denote by sys of let's say RPN F, this is the minimal length of closed geodesics, non-contractible, closed non-contractible geodesics, then the systolic ratio, which is sys of RPN f divided by nth root of n factorial volume RPN f. This is bounded by half.
Sorry. Why are you assuming that the metric is reversible?
Well, I actually don't know any counterexamples for RPN when the metric is non-reversible, but on the torus, there are different systolic inequalities when you allow non-reversible metrics versus reversible.
But you don't have counterexamples for when the metric is not reversible.
I couldn't find. I'm not fluent in the literature on this side of the story, so maybe someone else knows. But I couldn't find any counterexample for. One of my hopes, I should say, that failed was to try to use Reb dynamics to find counterexamples for this thing, but I don't know how to do it currently. It might be possible. Okay, and I should say here that when I say volume, I mean the Holmes-Thompson volume that Alberto also mentioned. So whenever I say volume for Finsler metrics, so here, volume is Holmes-Thompson volume, which is good for both the symplectic and the systolic side, I should say. It's basically the volume of the unit cotant. So maybe I'll say volume Holmes-Thompson of a manifold in F is the integral. Well, for me, with this 1 over n factorial over the unit disk bundle, codisk bundle of M. So this is the unit cotangent bundle of M, and this is the standard symplectic form of the cotangent bundle of M. Okay. All right. Now, an important thing I should say about this RPN conjecture is that it's true in dimension 2. So that's a result due to Ivanov. Okay. So theorem of Ivanov is that RPN conjecture is true in dimension n equals to 2. So basically, you can think of it as giving another proof for the Muller conjecture in dimension 2. Oh, I forgot to say that the Muller conjecture was proved in dimensions 2 and 3. So it basically gives a positive answer to Viterbo for these symmetric products in R4 and R6. Okay. All right, and then the reduction from this RPN conjecture to Muller. So that's a theorem of Balashev and Sanev. Basically says that RPN conjecture implies Muller. All right. So as I said before, through this connection between Muller and systolic inequalities for flat billiards, there are several questions that we asked ourselves seeing this result, basically. And one of them is, can we do billiards with non-flat metrics? So maybe I should say it like this. So this means RPN conjecture gives systolic inequality for flat, reversible, Finsler, and I should say symmetric too, like the table should be symmetric. Billiards. What about the same conditions but non-flat? In the end, I'll mention some other questions that kind of we thought or are thinking about in this context. Okay, I should say that when the metric is, so notice, saying like, looking at a billiard table KF, when F is non-flat, this is like looking at X, which is the unit cotangent bundle, but X is not a product. So X more general than product. So let me give some examples. So the first example is, let's look at X being a smooth domain, right? So these products are not smooth. What if X has smooth boundary? So if we look at a smooth, let's say, symmetric, so a smooth convex domain in R2n that has this Z2 times Z2 symmetry, okay? So we still want to keep the symmetry, but we are looking at a smooth domain, then if you think of it as a unit cotangent bundle of something, it's a unit cotangent bundle of a Finsler metric, I mean on some convex table, but the Finsler metric vanishes on the boundary of the table, okay? So this is a unit cotangent bundle of some convex table and reversible Finsler metric, but it's degenerate at the boundary. So F in the boundary of K is 0. So maybe a way to picture it is like, maybe I can draw it here. It's like a hot air balloon or something, right? Something like this. So this is the boundary of K. On the boundary, distances are 0. Okay, so maybe I should say that if you think of it as in terms of, I don't know, a metric space or a billiard table, it's very, very different than the flat case. So in particular, in the flat case, the table is geodesically convex with respect to the flat metric, because being geodesically convex with respect to a flat metric is just being convex in Rn. And this thing is very much not geodesically convex. Also, maybe I can say something about this reduction. Where is it? So this reduction, kind of a translation of what it does to this billiard table, is you can imagine it does something like gluing antipodal points of the boundary. Okay? And then you have something that is topologically a disk. You glue antipodal points, you get RPN. Okay? I'll say more about how you do it, but this is roughly the idea. If you look at something like this, it really doesn't care that you glue the antipodal points. Systoles on this RPN that you get will not see the billiard trajectories on the table. So this is kind of an example that I don't know what to do with. It would be definitely interesting to know what to do with it. Another kind of example is to take something that is relatively close to products. So maybe let me say it like, so close to product. And in what sense do I mean? I mean that, well, if I view X as unit cotangent bundle of some table and some metric, then I want this to be geodesically convex. Maybe I'll write in parentheses strictly, but just to be on the simple side of things. Okay, I'll give a definition in a moment, but let me just draw a picture. So, for example, if K is a disk, and the metric is like the hemisphere metric, but you're slightly less than a hemisphere, then that would be good. Okay, so maybe a picture is like, if this is K, then it's something like this. This is X. Okay. So let me give a definition. So let's say that a Finsler metric, or a Finsler manifold even, sigma f with boundary is strictly geodesically convex if for every 2 points they are connected by a unique length minimizing geodesic through the interior. So again, an example is, well, if your metric is flat and your K is in R2N, then just it's the same as strict convexity. Okay? All right. And then let me say a notation, and then I'll say, yeah?
That doesn't work if you take the visible on the whole hemisphere. You need to have
It's probably okay. But I should say that we're now in the process of like understanding the kind of simple generalizations of what we have written down. So I'm giving kind of the most simple case of things, but it's probably a little bit more general than that. And there are advantages of relaxing this strict geodesic convexity. I'll say more about it later on. Okay, so a notation is, let's take this Reb systole notation, C, and just use it for billiard systole. Okay, so notation. Well, let me denote by C of sigma f. This is going to be the minimal length of a periodic F billiard trajectory on sigma. Okay. So basically, it turns out that in this case, the RPN conjecture still implies this sharp systolic inequality for billiard tables with respect to geodesically convex or strictly geodesically convex metrics. But with this double symmetry that I just erased. But it's okay, I'll write it again. So, all right, so this is the theorem that is joint with Julian Chaitis, and it's in progress. So basically, suppose that F is reversible, Finsler metric on the ball, Bn, that's the unit ball, and assume that it satisfies the following conditions. So the ball is strictly geodesically convex with respect to it. That generalizes K being convex, F being flat. And now we have a condition that generalizes the symmetry. So let's assume that it admits, well, if that's confusing for you, just assume that it's symmetric under this Z2 times Z2 action, but admits an isometric involution. Let's call it phi. That has no boundary fixed points. And for simplicity, let's assume also that it isotopic to minus identity on the boundary of the ball. Then under these conditions, the systolic ratio for billiards, so is bounded by twice times the systolic ratio on RPN. So let me write here a supremum over reversible metrics. F tilde, let's say, and then I have a systolic ratio for RPN. And, well, maybe I should say that this RPN conjecture says that this is bounded by 1, which is the optimal constant for the Viterbo inequality. Okay? Maybe I should remark that since we allow for non-flat metrics, there's no advantage of allowing other tables than the ball. So it's enough to consider the ball instead of a general convex domain K, because we can just pull back by a diffeomorphism and it will still be geodesically convex. So that's why I wrote it for the ball. Okay. I have a little bit of time. Any questions? If not, then I'll say.
Could you do the other way around? Like have a convex set and all geometry on it? Like in the flat case?
Yes, it will just not be flat anymore. I mean, whenever it's not an ellipsoid, then you can't pull flat to flat. If you have flat on one side, it's going to be non-flat on the other side. Yeah. Okay. So let.
About this conjecture, you
Yeah.
said that if you don't assume that the metric is reversible, you think you don't have an example, but you think it's not true, right?
Well,
In principle, yeah.
I don't know,
Yeah,
but I wouldn't bet that it is true.
Yeah. But you think that you still have a bound.
Yeah.
Maybe not this bound, not 1/2, but some bound.
I actually,
The assumption that the
I
method
don't-
is reversible.
I don't know if it's true, but I would guess, based on examples, that it should be. Oh, you have this. Right, right.
You know what is a bound?
It's Roger-Shepard inequality.
Okay, okay. What?
It's a Roger-Shepard inequality where you symmetrize complex
But considering non-contractile orders. Yes. Sorry.
No, thank you for the question. Okay, so let me say a few words about the proof, and then I'll talk about some generalizations or extensions or things we're thinking about or things we failed to do. Okay. Okay, so idea of the proof. So the proof, roughly speaking, follows the following scheme. So we have this billiard systole, and then we bound it in terms of the width of the table. So roughly speaking, the minimal distance between two antipodal points with respect to this involution. And then we basically follow the scheme of Alvarez, Beba, Balachev, and Sanev to relate this to the to the RPN systole. So. Okay, so in a little bit more words, so we can define the width of sigma f and this isometric involution to be just the minimal overall points in the boundary of the distance with respect to f from x to phi of x. And since we don't have boundary fixed points, this is positive. Okay, so the first claim is that this billiard systole is bounded by twice this width. So that's basically like defining some functional, like just you take this distance and then the minimum, the derivative vanishes, and then you play with it and you use the fact that phi is an isometry to get a critical point of the length functional that was defining the reflection law. So basically, this is just showing that the width is a two-bounce billiard trajectory. Okay. Then the second claim, so this is claim 1. Claim 2 is that this, well, if under the assumptions of the theorem, for any epsilon, there exists a reversible Finsler metric on RPN such that, well, basically it gives us an approximation of the systolic, of a bound of the systolic ratio. So basically the width is bounded by the systole of RPN. with respect to this new metric. And the volumes are very close. I want to say, what is the size of the inequality? So this is greater or equal than the volume of RPN. Okay, so that's enough to prove this systolic inequality. Systolic ratio bound or something. Okay, so how do we do this? Well, basically, so maybe I won't write it down, but basically, we use this involution to glue antipodal points on the boundary, like phi antipodal points. There are two, it's not immediate kind of to finish the proof after you glue, because this F that we had on the billiard table doesn't descend to a smooth Finsler metric on the quotient. So that's like one issue, but it's not difficult. You just interpolate near the boundary with something that is nice, like the hemisphere metric. And then another problem is that systoles, and that's a serious problem, that systoles on, well, not in this case, but if you want to generalize, systoles on RPN might intersect RPN minus 1, which is the image of the boundary of the ball, several times. So these two bounds, maybe I'll draw a picture. So we have this ball, and then we have, let's say the width is this. Okay, so this is the minimizing x. We have a 2 bounds billiard trajectory that is exactly the width of the table, and then we glue to go to RPN. Any such billiard trajectory intersects the RPN minus 1 here. So we have an RPN minus 1 here, which is the image of the boundary of the ball. So it's not, maybe, I don't know how to write. Okay? So we have an RPN minus 1 here that is the image of the boundary of the ball, and billiard trajectories like this intersected once, right? So we glue these points, we have one intersection. But non-contractible loops in this RPN might intersect this guy several times. And then these are not coming from billiard trajectories here. So it's not immediate that the systole here gives you a bound on the systole here. But basically what saves us is the symmetry. So when the table is symmetric, it's not efficient for the systole to intersect several times. Okay? I don't think I will write it down, but this is kind of roughly the idea. Okay. So maybe I'll just take 2 more minutes to write a few kind of future questions or, whoops, or remarks. So what's next? So first is this, basically I said a lot of times during the talk that the symmetry is important, this double symmetry. So symmetry. So Pazit's going to tell us on Thursday that we cannot remove the symmetry completely. Okay, there is no hope to get such an inequality without it. But we can ask ourselves, what about like less symmetry? Okay, so not none of at all, but like, so the question is like, what about if we have just Z2 out of the Z2 times Z2? So it would be interesting to try to relate something that has a Z2 symmetry, for example, like it's symmetric under reflection in P, but not in like Y, but not in X and Y, to systoles on non-contractible manifolds, simply because if you have just one symmetry, it's like saying the metric is reversible, okay? And we know that reversibility matters in systolic inequalities, but this scheme completely falls, so you can't do it this way. So we're not sure how to do it. Something that we think should be possible with a similar scheme is to relax a little bit the geodesic convexity and allow for billiard tables that have topology. So billiards with topology. So for example, your billiard table could be a T2, and then you remove a disk, and then that should relate you to some systolic inequality on T2 connected sum with RP2. Okay? Roughly, that's the idea. So that's something that we're trying to do. And then the last thing that we're trying to do is basically find other constructions that relate, let's say, RAIB data to topology, to non-contractible loops. Okay, if anybody's interested, I can say more about it privately. Let me stop here. Thanks.